or acquires a synchronization object, the spin lock, which causes the, whoops, oh, my drawing went away. Okay, let me go back. So here's the page memory. And it raises the RQL right here by allocating or acquiring the spin lock to dispatch level. And then it executes a few instructions, and then it goes and references what it just wrote. For the system to detect that this is a violation of the do not touch pageable memory at a higher RQL, that piece of memory has to be sent out from RAM, and it's a lot easier to draw when we're not terminal servered in, so I apologize for that, although I'm not a very good screen drawer to begin with. The page of memory would have to be taken out of RAM between point A and point, by the way, I've got a rule, if you've been to my previous sessions, and I've collected some good phones. The ring at the end of the session that had the best ringtone, the phone with the best ringtone, I get that phone. So I'll let that one go because you might not have been aware of the rule. But please turn on your phones, okay? Especially if you have a Motorola Q phone. I really want one of those. So the bug, the only way that this is going to get caught, the only way that this is right here going to generate a page fault is if that page of memory, for some reason, got removed from RAM between those 2 points, and that would cause a page fault here that the system would say, hey, you're violating a rule, I'm going to crash the machine. What the force RQL checking does is causes just that. Anytime a driver raises the RQL up to above passive level, dispatch level or higher, the system goes and marks all of the page memory as not valid. It's still there present physically, but there's no connection between the virtual memory and the RAM. And that means that there will be a page fault, and that driver will be caught right then making the bad move. So force RQL checking is a very powerful option. I/O verification, the next one here, just checks the I/O packets that drivers send to each other and get from the I/O system. Enhanced I/O verification, some more rigorous testing. Deadlock detection detects problems with use of synchronization resources and drivers that might cause hangs. DMA checking, use of I/O system routines for direct memory access devices. Low resource simulation, you're not going to use that for crash analysis because that is used for testing a driver's ability to be out of memory, and you're not really wanting to stress drivers, you're wanting to catch them doing something bad. And then finally, disk integrity checking. That option was introduced in the 5.2 version of the kernel, which is the kernel used on 64-bit XP as well as Server 2003, so you won't see this on 32-bit XP. But this option causes disk blocks when they're written out to disk to be checksummed, and then checksummed again on the way back, and if there's a discrepancy between what the system saw on the way out from what came back, the system assumes that there's disk corruption going on and crashes the machine. So the crash analysis recipe is going to have you select all of these options except for low resource simulation. The next page is going to ask you which drivers you want to verify. And it's going to, again, give you some options here. And this is where the crash dump analysis recipe comes into play. Let me just show you this, and then we'll switch back to the slide that explains that. Automatically select unsigned drivers. That's going to be one possibility for the crash analysis recipe. This one you're never going to use. This one you're never going to use. So this is the other one that you might use. And if you select that one, you get taken to a page that lists all the drivers present on the machine and lets you check them individually. So let's go back to the crash analysis recipe now. Which is shown right here. First step, if you're getting crashes you can analyze. Point the verifier at any drivers that you suspect might be causing the problem. Recently updated, known to have problems. If you still get unanalyzable crashes, so you're still getting those crashes pointing the finger at stuff you don't trust, then move on to step 2. Select all the settings you did for step 1, but go down that all unsigned drivers path that you saw the verifier give you the option for. If you're still getting unanalyzable crashes, last resort, go after all the drivers, but do them in groups of 10 to 20 at a time. The reason why you don't just want to say all is because you're going to be doing two things. Crippling the performance of the machine, and if you want to see what it's like, go ahead and try it, see how long it takes your system to boot with this on. And 2, you're going to be crippling the effectiveness of the verifier. One of the options, the special pool option, becomes basically useless if you select more than a few drivers, and you'll understand that in a minute. And then last option, run the Windows memory diagnostic. Or you can do that at any point, of course, to see if really it's a memory issue. I'll talk about that shortly. So I'm going to show you two examples that transform an unanalyzable crash into an analyzable one, starting with the buffer overflow. So buffer overflow is a very common bug for Windows programmers that program in C or C++. Very easy to accidentally go off the end of an array, one entry too far. And if you do that in a driver, you go past the end of your driver buffer and you end up either in the pool tracking data structures, the heap manager structures, or another driver's buffer, which is the case that I described in that scenario where you've got your CD-ROM player and your audio driver. There can be a really long delay between corruption and detection. Let's go see just how long the delay can be. So I've got the VM here ready to go. I'm going to select buffer overrun. Every time I press the debug button here, I've corrupted memory. Let's see if I can get the mouse to move over there. Here we go. One. Oh, that time it happened right away. Nope, actually, I had the wrong VM resumed. Apologize for that. Let's do that again. So buffer overflow. And OK, here I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. When you get tired of doing this, or when I get tired of doing this, which I'm getting tired right now, I just run IE. Take a second. This VM is still restoring, so IE is going to take a second to start up. Here we go. And you know what? When IE doesn't do the job, then I fall back on trustworthy old Windows Messenger. And there we go. So that illustrates just how long of a delay there can be between this kind of bug and the problem that caused it. The problem it causes, actually. So how do you debug these things? Well, if you turn on the verifier and you point it at that driver that just caused the problem, my fault, and you do that using the crash analysis recipe, you're turning on special pool. And that means the driver is being verified. When they allocate memory, they don't allocate it from normal pool. They allocate it from a special region of memory, hence the name special pool. This special region is like a checkerboard. Every other page is invalid memory. And the driver's buffer is aligned against the top of one of these pages. By the way, this whole special pool concept's been taken to user mode, too, with the app verifier. The driver now, when it goes off the end of its buffer, boom, right here, invalid page, page fault, system's going to detect it right away, and it's going to crash. And this special pool, like I said, is the reason why you only want to verify a subset of drivers at a time. Special pool is a very limited resource, and if you went and turned the verifier on all drivers, once special pools run out, drivers get their allocation satisfied from normal pool, which doesn't have this kind of error checking in it. So you might miss the problem altogether if you're verifying the driver. If the driver that is causing the problem has its allocation not serviced from special pool. By the way, this is one of the options, one of the few options you can enable without rebooting the machine. So let's go back and do that same crash, except this time with the verifier on. So buffer overflow, and this looks the same way that I just showed you. I press do bug, and bam, crash. Now, what I didn't fail to show you before was the crash analysis of that first crash, and let's compare that with the crash analysis of that second crash, the first one being the one that had the long delay. And by the way, I've saved these crash dumps off from earlier versions of that crash. So here's buffer overflow and the crash analysis engine. Let's go ahead and do an analyze-v, but if you quick reader, you can see it's pointing the finger at a driver already. For some reason, I can't get the, here we go, analyze-v. And if you scroll up, the stop code is driver corrupted pool, which makes sense given the circumstances. And if you look down at the stack, here you can see the weighting at play, because there are three modules, three components in this stack trace. There's the HAL, the hardware abstraction layer, there's NT, and then there's this RAS-ACD driver. All of these are components of the OS. But the weighting says that RAS-ACD is more likely than either HAL or the NTOS kernel to have caused the problem, and hence it pointed the finger at RAS-ACD.